All right, I haven't made out the test yet, so I don't know what the free response are going to be, but it will be a capacitor circuit like we've done before. I can do one of those today, can show you, like as on the last semester's test in the free response. It'll be a combination resistor circuit, like in the free response from last year, if you look at last year's exam. And it might be a potential, it probably will be a potential problem as well. But I'll let you know more about that tomorrow in class. But you can sort of tentatively plan on those. And then the multiple choice will be as usual. There'll be 20 multiple choice questions. They're sort of evenly split between the different chapters. That is chapter 2, chapter 3, and then the first part of chapter 4. I uploaded the concept test yesterday, last night I think, for those chapters. Those are good things for you to look over. Looking at the old exams will help too. Looking over your notes will help. Okay? Particular things you want to look at today? Austin?
There's I think it's a free response on 19, and it asks about where the current is flowing. I don't know if that's going to be on the exam or not. I think it mentioned something about the loop rule, and that's confusing.
Okay, yeah, because we haven't gotten to the loop rule. So that was exam 2, spring 19, I think.
I think so.
Yeah, so if you see a circuit like this, let me tell you how you can identify these in the exams. If they have 2 batteries. If they have 2 batteries, you're not going to see it on the exam. Okay, that's called a multi-loop circuit, and we'll do those after this exam on Wednesday of next week, but not on this exam. Yeah, so you should have been confused. I'm glad that you were. Okay, you want to do resistors? You want to just do this problem? Why not? All right, so this is a pretty good indication of what your free response is going to look like, except you'll probably also have a collection of particles, and I ask you to find the potential. I might ask you something about the potential energy or the work required to place a particle there. We'll talk more about that tomorrow. Let's look at the equivalent resistance of this circuit, and then also it asks for the current through R4. But if you find really the current through R4, then you should know the current through all of them. So let me zoom in a little bit. I start with the part that is either in parallel, like that, or is in series. We did one similar to this the other day in class. Was it the same as this? It's sort of, they all run together, don't they? But nonetheless, it's still useful. So I can redraw this. This is 6. Oops, I said 6 and I wrote 2. 6 ohms, that's 2 plus 4. That's 2 ohms, and that's 3 ohms. 2 ohms and 3 ohms. The reason the 3 and 6 is 2 ohms because it's 1 over a third plus a sixth is equal to 2. And then that goes back to my battery, 12 volts. Now I do the 2 and the, I'm sorry, that's a 1 ohm right there. Y'all got that? R6 is 1 ohm. I do the 2 and the 1, and so I have my 12 volt battery, my 2 ohm resistor, and I have a 6 and a 3 in parallel. And then the next step, which will probably be your last circuit to draw, is going to be a 2 ohm and a 2 ohm with a 12 volt battery. Okay? Now, if I want to sort of go through the full process, I would say that 2 and 2 in series is a 4 ohm resistor. I'll just go ahead and redraw that circuit. So that's my equivalent resistor, 4 ohms. In fact, that's going to be the answer to this problem, is 4 ohms. And if I have 12 volts acting on a 4 ohm resistor, V is equal to IR. So here, I is going to be equal to 12 divided by 4, or 3 amps. That means resistors in series have the same current, and they have the same current as the equivalent. I will have 3 amps of current here, and 3 amps of current here. That means that I will have 6 volts of potential there, 2 times 3, or 3 times 2, I times R is equal to 6. And then I'd have 6 volts here. But notice that I could have just said, oh, I have 2 identical resistors. It splits up that voltage evenly. So I'm going to have 6 volts on both of those. All right, now I can begin stepping back. I'm going to write my voltages. I know this has to be 6. I know this has to be 6 volts. And then this whole thing right here also has 6 volts, because the equivalent is this 2 ohm resistor right here. So if that has 6 volts, then I know each of these resistors also have 6 volts, because resistors in parallel have the same voltage, and they have the same voltage as their equivalent resistor. They share the same voltage. Resistors in series split it up. Resistors in parallel share. Split and share. So 6 volts here, 6 volts on the 2 ohm, and then across these 2 resistors, the 2 and the 1, I have 6 volts. And just like I did down at the bottom, I can figure out the current going through those 2 resistors. The current through this resistor, 6 divided by 3, is 2 amps. So that means I have 2 amps here and 2 amps there. And then I can figure out the voltage. Once I know I and I know R, that gives me a voltage of 4 and 2 volts. Now, I could have said, oh, I have one resistor twice that of the other. I know the total has to be 6. And so the voltage has to be one number that's bigger than the other by a factor of 2. That's 4 and 2, but that have to add up to equal to 6. Okay, so 4 and 2. I still don't have the answer that I need, which is the current through R4. See, I asked R4 because I knew you'd have to get every current in order to find the current in that particular resistor, and that'll probably be the same on Monday. But R4 is within this parallel branch, and the equivalent of that one was this one right here. So the voltage across that parallel branch is 4 volts. That means each of those has 4 volts, 4 volts here, and 4 volts here. That means R4 has a voltage of 4 volts and a resistance of 3 ohms. I is equal to V over R. That's 4 over 3, or 4/3 amps. And so that would be the answer. There's lots of little bitty steps that take place in these circuit problems. And so for me to be able to give you partial credit, I need to sort of see how you're thinking. So be careful as you're working these out, on the free response especially. On the multiple choice, if you just want to do it in your head, I don't recommend that. But if you want to do that, that's fine. It's, if you get it wrong, you get it wrong. If you get it right, you get it right. But on this, if I see your work, then I'm much more inclined to give you partial credit if you have the answer wrong. Okay? We can do another one of those in a bit. But you want to look at the capacitor problem too? Those work out similar, but they're a little different. I'm going to erase this part right here. Hopefully by now, like many of you are pretty good at just looking at the circuit and figuring out how the voltages are distributed. I think that might be true for many of you. But if it's not, that's okay. Like, you can still work these problems. It just might take you a little bit longer. Really the difficult part with these is seeing how the circuit is laid out, because it looks kind of funky. And the funky part is this thing right here. And I want you to realize that because I have no devices in the nether regions in between the 2 junctions, that I can collapse all of this down to a single junction, to a single point, because there's no electrical devices. So even though it looks like I have these 3 different junctions, I really just have one junction that splits into 3 paths. And so if I were to redraw this circuit, then your circuit will look a lot like this. I might flip the 2, and you might have different kinds of, different numbers of capacitors, but it's going to be really similar to this. I would first just redraw it, starting right here, going through the circuit. When I come here, I notice that I have 2 branches in that junction. And so I'm going to split it up into two branches. I have the 2 microfarad and the 1 microfarad. And then it closes. When it comes back over here, I see that all this can sort of collapse down to a single point. And that's what I did. And then that breaks into 3 separate branches. And on those 3 branches, I have the 2, 1, and 3 microfarad capacitors. 2, 1, and 3 microfarad. Okay? And then it goes back to the battery of 12 volts. This is 2 microfarads. So remember with capacitors, these add up differently to find the equivalent. When they're in parallel, you just add them up. So this is 2, this is 3, 2 plus 1 is 3, and then this one is 6, right? 2 plus 1 plus 3 is 6. So I have 3 capacitors, 2, 1, and 3, or 2, 3, and 6 rather. Redraw those. 12 volts, 2 microfarads, 3 microfarads, and 6 microfarads. Now I can sort of think about what these are going to be because I know that the big capacitor is going to have the smaller voltage and the small capacitor is going to have the bigger voltage. I just want to keep that in mind, and then when I figure out what the voltages are, I'll just double check to make sure that that's true. You might be able to tell what the voltages are going to be. Can y'all tell? 6, 4, and 2. That's right. And I throw that out because, like, if this has, say, 6 volts, then this would have 6 volts. This would have 2 volts, and this would have twice of the 2 volts. We'll work it out. So these 3 capacitors, 1 over 2 plus 1 over 3 plus 1 over 6, to find the equivalent, that's 3, 6 plus 2, 6 plus 1, 6. 3 plus 2 plus 1, that's 6. So that's equal to 1. So the equivalent of this is 1 microfarad, 12 volts. And so I can figure out now what is the charge on this capacitor. It's kind of like what we did with the resistors, but at this point we figured out the current for the resistors. There is no current with charged capacitors. There's just no current flowing. But there is a charge stored. And so the charge is going to be 12 microcoulombs. Q is equal to C times V. 1 microfarad times 12 volts is 12 microcoulombs. And then just like with the resistors that all have the same current when they are in series, these all have the same charge. Microcoulombs, 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 12 microcoulombs. Be careful again, students get confused here because we have a variable for C, which is for capacitance, which has units of farads, and then we have the variable Q, which is in the units of microcoulombs. So sometimes students get capacitance and the coulombs sort of mixed up in their heads because you're not real familiar with them. So just be really careful, recognize that that's the case. I find that it's useful to write both the variable and the unit out so that you can keep those straight in your head. Once I have the charge and the capacitance, I can figure out the voltages. V is equal to Q divided by C. So that's going to be 6 volts, 6 volts, and 6 volts. No, I'm sorry, not 6, 6, and 6. 6, 2, and 6, 4, and 2. Where's my eraser? There we go. 6, 4 volts, and 2 volts. Okay, you with me? It's a lot of questions on your test. I want to make sure y'all get this right because this will probably be, what I usually do, 8. It's probably be 5 to 6 questions for the free response, and then you'll have a few questions within the test too that'll be similar. That's a lot of the test circuits, or most of the test. I can add those up. 6 plus 4 plus 2, that equals 12. I'm doing great. Now, these all have 6 volts on them. This thing right here, which is in parallel, both of these have 6 volts. And then these all have, these have 4 volts. Sorry, it's been a long day, y'all. Four volts, and then these are 2 volts. 2 volts, 2 volts, and 2 volts. Now I know the voltage on every capacitor. I can figure out the charge on every capacitor. It's just Q is equal to C times V. So the charge on this capacitor is 12. The charge on this capacitor is 8, 4, 4, 2, and 6 microcoulombs. So you can find the charge or the voltage on any one of those capacitors. And that's what you'll need to do on the test, is be able to find the voltage or current on a resistor, or find the charge or the voltage on a capacitor. Okay, dokie? Yeah, Logan?
Is that what the 2 free responses are going to look like?
Yep. Yep, your 2 free responses look like that. There'll probably be a third too. There'll be a collection of particles. And I'll ask you what is the potential. And then I might ask you too, I haven't decided that, I'll tell you tomorrow. I might ask you too about the work required to bring a particle into that potential. That's pretty straightforward. It's just the work is equal to Q times delta V. We'll look at that tomorrow in class. So make sure y'all come to class. We'll review more for the test tomorrow. Okay? 100% on the free response. That's what I always shoot for. You know, we get 100% on the free response. You can do that, right? Everybody 100%. Just say yes.
Yes.
Yes. Good. And if you can do well in the free response, then you're probably going to do well in the rest of it. Can I clear this? Good indication of what you'll see on Monday, right here. I don't want the free response to be a secret. As I said, if you see any circuits that have 2 batteries, like here and here, not on the test. That's the second part of chapter 4. Or anything that talks about, well, let's just look, I can show you. So like in this test, when you get like here, not on the test. When you get to funky things like this, not on the test. That's it. All right, let's sort of stroll through this test. This one's a good, and we can look at exam 1 too. But notice that you have capacitor circuits. Let's look at number 5. We're not going to work it. I just don't want you to be freaked out if you come to a question like this, because sometimes we don't draw the battery. But that circuit would be the same as that. It's asking for what is the equivalent capacitance between this point and this point. You can imagine then that there's like a battery hooked up to those 2 points, and then it would just be a matter of finding the equivalent capacitance. Also, don't be freaked out from the way that it's drawn. Like the way that I would draw this circuit normally would be where I have 2 capacitors up here, 1 capacitor right here, and then 2 capacitors right here. That's the same circuit. Okay. And you can tell because I just looked for the junction. This, not a junction. This is just a bend in the wire. It's not a junction. Sometimes students think this is a junction because it's a bend in the wire, but it's not. And I can tell because there's only, there's no extra wire there. It doesn't split into any parts. To be a junction, it has to split into different parts, 2 or more parts. Okay, so don't freak out about that. If you see a circuit with no battery, I'm just asking you for what is the equivalent capacitance or resistance of that circuit. You'll see some simpler circuits like this that were sort of like what you had on the free response. You'll see some questions about sort of the capacitance. How do you change the capacitance, the capacity of a capacitor to store charge? Looking at its area and the distance between its plates and the dielectric. You'll see some similar questions about resistivity and the dimensions of a resistor, like number 13 and 14 there. You might see a question about power, like number 11. And remember that power is equal to V times I. Or you can do the V squared over R or the I squared R. But all three of those are on your equation sheet. But power is 100, V is 150 times the current, which is what I want to find. And so I is 1 over 1.5. That's 2/3. That's 6.67. Yeah, number 15. No, I'm not going to do it. We didn't do one like this. It's a little bit different than ones we've done before. When I gave this on the exam, we had done a circuit very similar to this one. So you can just not worry about 15. Is that okay? Are you worried? Okay, good. You might have one like number 16. You will have one like number 16 where I ask you about the lowest voltage or current. We did some like this last time in class. And I like them because you have to look at it. You can work it out. Actually, you can't work it out here because I don't give you a voltage. But if you really want to work it out, you can. You can just assign some voltage, 12 volts or whatever here, and then go through the whole darn process. But if I think about this, which one has the lowest voltage? Here I have a 6, a 3, and a 2 in parallel. We're getting pretty familiar with that, right? A 6, 3, and 2 in parallel. What's that equivalent to? What was it 2? It was 1, 6 plus 2, 6 plus 3, 6. It's 1, right? So these 6, 3, and 2 is equivalent to a 1 ohm resistor. And so I have a 1 ohm and a 1 ohm. And so those are going to split up voltages evenly. Whatever voltage I have here is going to have the same voltage here in this branch, and this branch. So can you tell me which resistor has the smallest voltage? R what? R3, that's very good. R3. R3 because I know that I have the voltage across these two resistors, but it's split up into two different parts. And so both of these are going to have a voltage that's less than any other resistor. And because R3 is a smaller resistor, it's going to have a smaller voltage. If you wanted to do numbers, you could. You could say, all right, I got 12 volts here. So that means I have 6 volts here, 6 volts here, 6 volts here. And on R3, I'm going to have 2 volts, and on R4, I'll have 4 volts. The voltages will split up in that way. Be ready for one of those questions. I could also ask you, what would I ask you? Which resistor has the smallest current? Which resistor do you think has the smallest current? R1? R1 is actually going to have the biggest current. Because all the current coming off of this battery is going to go straight to R1. I appreciate that's what you meant. That's what you thought I said, the biggest current, right?
No, it's wrong.
Okay. I appreciate that. So R1 will have the biggest current. Which one will have the smallest current? One of these. What did y'all say? R what? Yes. High five. All right. R2 has the smallest current because I'm looking, I know that all that current is split up here. The smallest current is going to go through the biggest resistor. That R2 resists the flow of electricity the most, so I get the smallest current. I would expect a couple questions like that. We started them last time. We'll probably do one or two more. They were in the concept test towards the end. We'll do a couple of those in class tomorrow, but they're also on Moodle now, so if you want to get a preview, that's fine. All right. You want to look at some other tests? Are there any particular questions? Let's look at exam 1, just get a, so could see questions like number 3 and 4 here. where you have to find the potential at point A, and to find that, what was that top charge? 25. So to find the potential at point A, I would say V1 plus V2. That is 9 times 10 to the 9th, 9 times 10 to the minus 9. That's this charge right here, divided by the distance, which is 3, plus 9 times 10 to the 9th, 9 times 10 to the minus 9, divided by, no, it was 25, right? Negative 25. Divided by 5 meters. Thank you. Don't put this in your calculator. Go through and make all the cancellations. It'll make your life a lot easier. That's 27 minus 9 times 5 is minus 45. That's equal to minus 18 volts. And so that's the potential at point A. You'll have to do something like that, where you have a collection of particles. I might also ask you to find, say, the speed of the proton, or ask you how much work is required to bring a charge into this point. That's just really going based on this, that E is equal to Q times delta V. That's based on our basic definition of what is V. V is an energy per charge. I'll do kinetic energy there just to differentiate between electric fields. And so I'd say a proton is 1.6 times 10 to the minus 19 times 18 volts, because it's moving, this particle that I'm moving. Wait, no, this is a separate question, I'm sorry. Let's say, though, let me change this question. Say that it follows up on question 3, where I'm moving a charge from a distance that's really, really far away to this position. So I have a charge that's over here, a proton, and I'm going to move it from here all the way up to where I am right here. And so if I do that, my change in potential for that charge would be equal to the final potential, which is minus 18 volts, minus the initial potential, which would be 0 volts. So I'd have minus 18 volts. So that's where I get my delta V from for that, because I'm moving from a reference point where the potential is 0 up to a point where the potential is non-zero. Okay? And now I want to find out the kinetic energy. The kinetic energy is this 1.6 times 10 to the minus 19, whatever that is, times 18. And then if I want to find the speed, I set that equal to 1/2 mv squared. Maybe something like that. I'll let you know tomorrow. It probably will be something very similar, but I'll let you know tomorrow in class. Okay? All right, let's skim this exam, looking at the chapter 2 problems. You'll probably have a question where I ask you, where is the potential 0? Is there one of those? Yeah, here's one, like number 16. Almost certainly have one of these. You want to find a point where you're getting far away from the big charge and staying close to the smaller charge. So here, it's going to be A, right? Oh, no, it's B. Yeah, B is the right answer. You know how I knew it was B and not A? It's a little tricky. So the point B is a distance, this distance away from the +2 Q charge. But the point B is 3 times that distance from the -6 Q charge. And this charge is 3 times as big as this charge, so you want the distance to be 3 times as far away. If I write down the potential equation, V is equal to KQ over R. My charge is twice as big, but it's twice as far away. as the plus 2q charge. And so those two factors cancel out. But expect a problem like that, where you're trying to figure out which point gives you a zero potential. Really, if you go through each point and sort of reason it out, you should be able to figure out which one would give you the zero potential. You know it can't be C, D, or E, because those are too close to the -6. So really you're trying to figure out, is it A or is it B? That's really what you're trying to discern. Okay? Probably see a question something like number 17 and 18, sort of as a series of questions. Number 18 was a lot like the one that we did before, where if you want to know the energy of the proton, it's equal to Q times delta V. And you just have to figure out what delta V is. Delta V, if I'm moving from point A to point B, then my delta V is 2 volts. There's a 2 volt potential difference between those two equal potential lines. All right, what else y'all want to look at? You want to look at some other exams? Okay. Look at exam 2, spring 18. I'll sort of scroll through here. Let me know if there's something you want to work through. Number 15. Which has that one? The toaster oven one? Okay, so which has the smallest resistance? You should be able to answer this, but really this gets later into chapter 4. So if you see any questions about household things, that'll be not on this test. But let's go ahead and look at this because it's still a useful thing. You won't see a question like this, but we should be able to reason it out. Which has the smallest resistance? If I have a small resistance, am I going to have a big or small current? If I have a small resistance to the flow of electricity, do I have a big or small current? I have a really big current. And if I have a big current, does that device put out less or more energy? It gives out more. If I have a big current, I put out a lot more energy. I just have the energy of the electrons is greater because they're moving, well, they're not really moving at a faster rate, but they're carrying more energy. And so the one that puts out more energy has the smaller resistance. And which one puts out more energy? The toaster oven. Toaster oven is a huge draw on your electric bill. It's like 1,000 watts. It's one of the biggest things, you know, apart from your clothes dryer and your air conditioner, the big items. It's, as far as devices, it's one of the biggest draws on your thing. So the toaster oven has a big current. So it has a small resistance. And the cell phone charger is almost no resistance at all. I mean, almost no current at all. You probably see one like number 18, where you're calculating the resistivity. Remember that was R is equal to rho L over A. And here you're just solving for rho and figuring out what rho is. Here is I, this is A, this is V. You can calculate R, which is V over I. That's equal to 2 ohms. And then the length was 1. And so you can solve that then for rho, which is going to be 2 times A, 5 times 10 to the minus 8, over L, which is 1. And so it's going to be 10 times 10 to the minus 8. Or iron is the material. Okay. Yeah. Probably give you a question like this where I ask you for the rules. Just make sure you know the rules pretty well. They'll look similar. So here, for example, resistors in series must have the same current. Just ask yourself for each one, is that true? Is that true? Resistors in series have the same current? Yeah, it is. That's one of our rules. Resistors in series must have the same voltage. Is that true for Nope, not true. For resistors in series, the total voltage across the resistors is equal to the sum of the voltage across the individual resistors. True or no? Yes, true. Yes, true. That's the V equals V1 plus V2. So This was I equal I equal I. This one's not true. This would be true for parallel. For resistors in series, this was V equals V1 plus V2. So yes, true, yes, true. For resistors in series, the equivalent resistance is always less than the smallest resistor. Not true. If it was parallel, it would be true, but this one's not. So it's 1 and 3. 1 and 3. Oh, B. Number 20, we did something like this the other day. If I removed one of these resistors, just took this away, what's going to happen to the current through the remaining resistor? Up, down, stay the same. It's going to stay the same because these two resistors are identical, or they have the same voltage. And so if I get one of these away, remember resistors in parallel are completely independent, then this one will keep the same voltage and the same current. Now, I could ask a different question, which would be, what happens to this current if I get rid of this resistor? And if I get rid of that resistor, then that means that my resistance, ironically, getting rid of a resistor actually increases the resistance when they're in parallel. And if I increase the resistance, then this current will actually decrease. Removing a resistor in parallel decreases the overall equivalent resistance because it takes away a path that electricity could flow, and so it's going to decrease the overall resistance of that circuit if they're in parallel and I remove a resistor, which is sort of counter to what you might think. When I add resistors, my resistance decreases because I'm adding additional paths for the electricity to flow. Oh, number 19. We did one like this, and students often get messed up on these. The resistance of wire A is half that of wire B. How do the resistivities compare? Oh, this one's not that bad. The resistance of wire A is equal to half, not the resistivity, the resistance, half of wire B. So I write down my equation, rho L over A, and I see that resistance is proportional to resistivity. It's a linear relationship and it's a direct relationship. So if RA is equal to half of RB, then rho A is equal to half of rho B. Whatever I do to one side, I have to do to the other side. So D would be the right answer. Be prepared for those. I'll certainly ask you a question about if I change this variable, what happens to these other variables? On this test, I actually chose I looked at some old MCAT prep books, and I chose some questions from those. But they're, good. But they're really similar. I mean, they're questions that I would have asked anyway. In fact, a lot of my questions are a lot like MCAT, old MCAT exams. So y'all can go to medical school if you want. No, don't want to go to medical school. No, that's okay. I don't either. All right, so battery has an ideal EMF of 12 volts. When 2 amps are driven by the battery, the terminal voltage is 10 volts. What is the internal resistance of the battery? So you could write out the equation and you could get it right, but let's draw a picture. The circuit looks like this. Actually, no, I'm sorry, because I don't have an extra resistor. It's easier just to write out the equation. So my delta V is equal to my EMF minus my current times my internal resistance. Remember these batteries, they're not perfect. They have some internal resistance. And when I put a current through those batteries, you lose some of your voltage. And so if my terminal voltage is 10 volts, but my EMF, my ideal voltage was 12 volts, when I apply 2 amps of current, that means that my internal resistance must have been 1 ohm. of internal resistance. You might have a power question like this, number 17. I have V, I have R, so power is equal to V squared over R. That's 9 over 10, or 0.9 watts. We haven't done these directly in class, number 11. Let's do one. You did them in lab, and you should know how to do them. So let's do this question. Okay? You follow what I'm saying? Did y'all see that? Okay. So I apply several different voltages across the circuit and measure the current that runs through the circuit. And I want to know what is the resistance of the circuit. So there's the way that you'll probably do it, and then the way that I'd really rather you do it is that the way that you'll probably do it is you'll say, okay, I'm going to take this point, I is equal to 15, V is equal to 30, I want to know R is equal to V over I, that's 30 over 15 or 2 ohms. And that would get you the right answer. But really what I want you to do is to write out the equation for this graph. I is equal to 1 over R times V. That's just from Ohm's law. Y'all did this in lab? Yes, you did. Yes, you did. Oh, you don't in lab. Okay. Well, the Y, this is my Y variable. This is my X variable. This is the slope of the graph. So the slope of this graph is equivalent to 1 over R. The slope of this graph is 15 over 30, right? Rise over run. So 15 over 30, which is equal to 1/2, is equal to 1 over R. That means if I solve this for R is equal to 2. And you might say, well, that's a lot more difficult. But I like for you to think about it in that way. So it's okay if you do it the first way. You'll still get the right answer. But I like for you to think about the slope of the graph. As scientists, you know, that's kind of important that you think about this way, because it allows you to take big collections of data and then extract very useful information about that data. Did you see? You got this? Okay. Can't wink very well. Oh, you'll have some stuff about voltmeters and ammeters, probably just 1 or 2 questions. The things you need to remember about voltmeters and ammeters. Voltmeters are hooked up in parallel and have a big resistance. Ammeters are hooked up in series and have a really small resistance. Voltmeters are used to measure voltages. Ammeters are used to measure currents. The resistance of a voltmeter is big. What did I just say? True, right? An ammeter is connected in series. True. The voltage across an ammeter is small. Not necessarily true. It can be true, but not necessarily. So we'll say it's false. It can, if the current is small and the resistance is small, which it is for an ammeter, then this will be true. But it doesn't have to be true. And the resistance of an ammeter is small. True. So 1, 2, and 4 is the right answer. All right. Remember, these are the tricky ones. The voltage across an ammeter is small. Not necessarily, you would say to yourself. And if it's not necessarily true, then it's not an answer to the question. Okay. We can do more. You want to do some more? We good for now? Is that all for today? No help session tomorrow, unfortunately. We have a big department meeting and stuff. Can I stop? Yeah, I'm going to do number 3. I'll just chill for a sec. If you double the voltage across the plates of a capacitor, how is the stored energy affected? So, energy in a capacitor, I don't know if y'all remember this, is 1/2 CV squared. And if I double the voltage across this capacitor, if I double this, I'm going to quadruple the energy. So the stored energy will increase 4 times. You'll probably see a question about that. You see all the same categories of questions. Like I have a rubric that I go by where I pick out the right number of questions. So almost always you'll see every topic covered on the exam that you see covered on previous exams. All right, make sure you see me. I think I got everybody except for you latecomers. So make sure.